Hello and welcome to the third part of Unit 15. In this part, we're going to look at Archimedes' principle. Okay, so Archimedes' principle talks about buoyancy. And what it says is that if we have an object in a fluid, either all the way or only partially, the force on that object is equal to the weight of the fluid it displaces. Okay. So here we can see an object in a fluid. We have an upward buoyant force and a downward weight of the object. If that object weren't there, then the force on that chunk of our fluid would be equal to the fluid that would fill that particular part of our container, however you want to think about it here. Okay. So Archimedes' principle says the buoyant force is equal to the weight of the fluid it displaces. So we can write that out, maybe. Going back one. Trying here. Okay, so the buoyant force is equal to the weight of the fluid displaced by our object. Okay, well, weight of the fluid is just going to be the mass of the fluid times the acceleration due to gravity. And I'm again going to pull on density, is mass divided by volume. So mass is going to be density times volume. So the buoyant force with that plugged in will be the density of the fluid times the volume of the object times the acceleration due to gravity. Okay. So now let's apply this to an example. We're going to look at an ancient Greek coin. But the cool thing about this example is it's how related to how Archimedes came up with his principle in the first place. So when Archimedes was alive, there was a king. I'm sure he had a name, but I don't remember the king's names. That was gifted a crown, and he was told when he was gifted the crown that it was made of pure gold. But it's very easy to deceive with gold, because if you take gold and mix in some other elements, it still looks like gold, right? And we can see that in jewelry, where you can have different like 14 karat gold versus 18 karat gold. It all still looks like gold, but there's a higher gold content in one of them, right? So Archimedes is tasked with figuring out, is this gold crown actually gold that the king was gifted with? And the famous story goes that Archimedes was in the bath. This is one of the public baths that they had back then, and had this epiphany about his principle here, and then yelled Eureka while running through the streets naked. It wouldn't happen today without him getting arrested, but that's what happened supposedly with Archimedes. So here we have a gold coin, and we are going to think about this gold coin in two different scenarios. One, when it's not in water. So in that case, it's going to have a tension force up, assuming it's dangling from a string, and the its weight going down. Oh, I wrote W instead of M because I was talking about weight, and there we go. Okay. And now we're going to think about that same coin when it is submerged in water. And now there's an extra force on it. There's the tension, there's the buoyant force, and there's still its weight. Now, as you might be looking at this going, those two T's are not the same. I agree completely. So I'm going to call this one TO because it's without the water, so O for without, and TW for T with the water, or TW for water. Okay. And if we come up to this one, assuming that it's not accelerating, we can use Newton's second law to tell us that TO will just equal the object's weight, our coin's weight. And we can come down here and again apply Newton's law that Oop, that's an O and it should be TW, plus the buoyant force has to equal the object's weight. But now we can make a substitution because mg is just what we had before. So now we have TW plus FB, the buoyant force, equals TO. Right? Which means that the buoyant force can be written as the tension in our string when the coin is out of the water minus the tension in the string when it is in the water. Okay. But we know what the buoyant force is due to Archimedes' principle. We know the buoyant force on our coin is going to be the mass of the water times, not the mass of the water, the density of the water, rho GH. Hold on. Pause, rho FG. So, yes, density of the water times G times the volume. I am getting this all mixed up. There we go. Rho GV. That will be our buoyant force. Okay. But we can rewrite this using density as just the mass of the water times G. Yes. I'm getting there. Okay. Which means that we can find the mass of the water by determining how much the mass has changed. So the mass of the water will be our mass out of the water minus the mass while submerged. I'm going with it. So that's going to be 8.63 grams minus the 7.80 grams. And that is 0.83 centimeters cubed. Okay. And the reason we can do that, remember, is because it comes down to the buoyant force is related to what we're measuring in those tensions. Okay. Okay. So we have the mass of the water. We can take and find the volume of the water by taking the mass of the water and dividing by its density. So that's 0. Did I really put units of centimeters cubed on a mass? Let's try again. Guys, I'm tired. It's 9:10 at night. So just bear with me. 0.83 grams divided by the density of water, which we're given as 1 gram per centimeter cubed, which gives us a volume of 0.83 centimeters cubed, which is what I was trying to do up above. I just skipped ahead in my notes. Okay. But the volume of the water equals the volume of the coin. So the volume of the water, oh my goodness, equals the volume of the coin. So now we can find the density of the coin is going to be the mass of the coin divided by the volume of the coin. And the mass of the coin is what it is when it's just in air. So that's our 8.63 divided by our 0.83 centimeters cubed, which works out to be 10.4 grams per centimeters cubed, which is equivalent to silver roughly, which is consistent with an ancient Greek coin. Okay, not sure I did the best job of explaining this, but the answer is correct. This ends this part of this unit.